Welcome to this puzzle guide. We'll be looking at the notion of a graph, and to motivate that notion, I will use the medium of a puzzle. So here is the puzzle. So we have a chessboard of this strange shape. This is not a traditional chessboard. And the problem is this. The problem is, suppose I want my knight to start here, and I'm asking the question if this knight can travel across, travel on this chessboard in such a way that it visits every square exactly once and then returns back to its original position. Right? So it's a very strange thing to ask, but anyway, let's say we ask that question, and this is the exact formalism. So can it start at a point and travel on the chessboard in such a way that it visits every square exactly once and it returns back to its original position at the end? Okay, and it's a knight, so it cannot jump arbitrarily. It jumps like a knight, so it jumps in an L shape. If you don't know how a knight moves, then you can just do a quick Google search or YouTube search and figure that out. Alright, so I do not want you to solve this puzzle or think about this puzzle. Just let me ramble on. So here is the thing. I label each square by a number, 1 up to 12. There are 12 squares. And let me isolate them as dots. So I will have an abstract representation of how the knight moves in a moment. But right now I just have these 1 dot per square. Right, so I have arranged them in a circle. Now, if we look at the knight, and suppose the knight is at this position, and I want to know what are all these squares that are accessible to the knight from this position. So I see it can go to 9, it can go to 6, it can go to 7, and that's all. That's all it can do. So I will connect 1 with 9, 1 with 7, and 1 with 6. Right, similarly, let me do one more. So what about, suppose the knight was here, then it can go to 2, it can go to 6, and that's it. So 8 will be connected to 6 and 2. And similarly, one can join all the other, vertices in the correct way. So if we do that, we will get a shape like this. So these will be all the connections as we see here. And now, if we look at this sequence, what is it saying? So suppose we start at 9 and then we follow, let me use some color for it. So suppose I use this horrible color, which is green. So we start at 9, then we go to a 1, then we go to a 6. So this is how a knight is jumping. So you start at 9, then you go to 6. Sorry, you can't go to 6. Then you go to 1 and then you go to 6. Right? So 1 and then 6. Or let me copy this just for reference. So you can visualize as I'm drawing the edges on the, drawing these green things, you can also visualize simultaneously. So then I go to 6 and then I go to 8. Then 2. Then 10. Then 4. Then 12. 7. 5, 11, 3, and then again a 9. So this will be the last. So I come back to the original position. So if you follow this around, in this diagram, so 9, then a 1, then a 6, then 8, then 2, 10, 4, 12, 7, 5, 11, 3, and then again 9. So yes, indeed it is possible. You can start at a vertex and start at a square and come back to the same square in a way that you visit every square exactly once in the process. So basically this representation of this kind of data into a much more manageable data helped us find this sequence. So to find this sequence, I did not use any deep mathematics. I just played around with this shape and I found it. Another advantage of doing such a thing is, suppose I wanted a computer to solve this problem for me. This was a very small chessboard, so one can do it by hand. But if this was a very big chessboard, let's say 1,000, some 1,000 squares were there, then I would generate this kind of data, feed this to a computer, because this kind of thing you can feed to a computer. How do you feed a chessboard to a computer? You'll have to develop a data structure, and what is more convenient than this? So you feed this to a computer, and then the computer can do a search and find such a thing. So basically this motivates the notion of a graph. Let me formally define a graph. So a graph is a pair v comma e, where v is just any set. It could be finite, could be infinite, and we call the elements of v the vertex set of the graph, or the elements of v the vertices of the graph. And E is a collection of two element subsets of V. Is a collection. It is not necessarily containing all the two element subsets of V. It contains some of the two element subsets of V. So another way to express this would be saying that E is, so what is the set of all the two element subsets of V? So this is the set of all the two element subsets of V, right? And E is a subset of it. So you pick any such thing which is a subset of that guy, and you make this pair. Any such pair is a graph on V. We call it a graph on V. And V is called the vertex set of the graph. E is called the edge set of the graph. So this is exactly what is happening here. In our situation, we had all these vertices, and the edges were those connections which allow the knight to jump from one vertex to the other. So 4 and 10 are connected because the knight can jump from 4 to 10 or from 10 to 4. So that's the graph that we get here, and then we are asking if in this graph you can walk along the edges in such a way that you visit every vertex exactly once and come back to the original vertex at the end. And this is a much more manageable thing than that. I hope you agree with me. So this is the notion of a graph, and let me just give one very silly example. So a complete graph. So if let's say V is equal to this set, most convenient set, and E is equal to all the two element subsets of V, then we say that the graph G is equal to V comma E is the complete graph. This is the definition. The complete graph on n vertices. So the set E could also be empty. It is not necessary that E is non-empty. E could also be empty. In that case, you get what is called an empty graph. So the edge set is very, very free. There is not much constraint. In fact, hardly any constraint on the edge set. And this is a hallmark of combinatorics, that there's a lack of structure, which you can systematically study and produce a lot of interesting theorems in. Alright, so much for graphs, and more lectures on graphs will be coming. But this is a very useful notion when thinking about mathematical puzzles that are usually asked in Olympiad problems and otherwise. So this will be occurring frequently in the puzzle sessions. Alright, so I don't want to belabor the point. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.